Today we're going to find the line integral of the vector field f over the curve C. So f equals sine y of I plus x cosine y plus cosine z j minus y sine z k. And the curve is r of t equals sine t of I plus tj plus 2tk. So, we want to use the fundamental theorem of line integrals to solve this. And doing this, we know that an integral over a curve of a vector field dotted with dr equals f of r of b minus f of r of a, b being the endpoint and a being the starting point. So in order to use the fundamental theorem of line integrals, we have to make sure that this function is conservative. To do so, we want to find the curl of this vector field and make sure that it equals 0. The equation, or the formula that we use to do this is r of y, or the partial derivative of r with respect to y, minus the partial derivative of q with respect to z, I, minus the partial derivative with respect to of r with respect to x, minus the partial derivative of p with respect to z, j, plus the partial derivative of q with respect to x, minus the partial derivative of p with respect to y, k. In this function, in this vector field, this is our p, this is our q, and this is our r component. So, we're going to plug these into the formula by finding all of these partials, and we want to make sure that it equals 0. So, the partial of r with respect to y is negative sine z, and the partial of q with respect to z is negative sine of z. This is plus. The partial of r with respect to x is just going to be 0, and the partial of p with respect to z is just going to be 0. So there's no z. Oh, forgot that. I. And partial of q with respect to x is cosine y, minus the partial of p with respect to y, which is also cosine y. So, as you can see here, we have negative, this is minus, sorry about that. So we have negative sine of z minus negative sine z, so that just turns into a plus, and those cancel out. And then we have a 0 and 0, and then we have cosine y minus cosine y. So that also equals 0. So this equals 0, meaning that the curl equals 0. So yes, it's conservative. Meaning, we can use the fundamental theorem of line integrals. So, to start off the fundamental theorem of line integrals, we want to find the potential function. So, we want to find when the vector field equals the gradient. Okay, so we're going to start off by taking the p component of the vector field, because we know that that is the partial with respect to x. So, use a different color so it stands out a little more. So, f of x, as you can see, or the partial with respect to x, is sine y. Now, we want to find the function, the potential function, but this is a partial with respect to x. So we have to take the antiderivative of this partial derivative. So we account for the x, that would be in this part. And we also have to account for the y and the z. Because if we were to take a partial with respect to x, something with just a y and a z and no x would completely disappear. So now we want to find the partial with respect to y. So we can try and solve the unknown. So the partial with respect to y is going to be x cosine y plus the partial of g of y of z with respect to y as well. Now, looking at this, the vector field, we know that the y component is going to equal x cosine y plus cosine z. So that's what the partial with respect to y equals. So to solve for the unknown, we're going to set this equal to this q, j, y component of this vector field. So that equals x cosine y plus cosine z. So, as you can see, this x cosine of y and x cosine of y equal each other, meaning that the partial of g of y of z with respect to y is just going to equal this cosine z. However, we want g of y of z, not the partial with respect to y. So, as we did earlier, we're going to take the antiderivative of this with respect to y. So, we know that this would have a y in it. And we want to account for the z component, as we did earlier, like we accounted for the y and the z. So we're just going to call that h of z. Okay. Now, similar to what we did before, we're going to take the partial with respect to z, this function. So that's just going to equal negative y sine of z plus h prime of z. And we know that the z component of this vector field equals negative y sine z. And now we can solve for our unknown, which is actually going to be 0, meaning the h of z is just a constant, which we'll call k. So, now that we know the h of z is just a k, and we know that g of y of z equals y cosine z plus h of z, and we know that the potential function equals x sine y plus g of y of z, we can put it all together and we know our potential function. So, our potential function will equal x sine y plus g of y of z, which is y cosine z, plus h of z, which is just a constant. So, we have our potential function. So we know the potential function that goes in our fundamental theorem of line integrals. Now, we want to solve for the starting and the ending point in the paths before we plug it in to the potential function. So, right here, we go from 0 to pi over 2, as you can see, And we have our path right here. So we want to solve for r of b and a. So we can plug it into our potential function and use the theorem. So we have r of a, which is r of 0, and that's going to equal sine of 0. I'm using this function right here, this path, plus 0 plus 2 times 0. And that will just equal, oh, sorry, I meant to put commas, sorry about that, because we're looking for a point. So we have sine of 0, which is just 0. 0 is 0, and 2 times 0 is 0. So r of a is 0, 0, 0. Now, we're going to solve for r of b, which is pi over 2. So we'll do the same thing and plug pi over 2 into our path. So sine of pi over 2, comma, pi over 2, comma, 2 times pi over 2. So this is going to equal sine of pi over 2 is 1, pi over 2, which is pi over 2, and 2 times pi over 2, cancel out the 2's, and it's just pi. So now that we have our r of a and our r of b, we can plug it into our fundamental theorem of line integrals. So that's going to be the potential function with these points that we solve for, because it's f of r of a and b. So I'll write it again right here. So just to remind you all that it's f of r of b minus f of r of a. So we'll plug those in. We can even do this. So this is our b. So f of 1, pi over 2, pi, minus f of 0, 0, 0. So we'll plug that into our function right here. Do a little, so we don't get these mixed up. And that's just going to be 1 times sine of pi over 2 plus pi over 2 times cosine of pi plus k minus 0 times sine of 0 plus 0 times cosine of 0 plus k. Okay, so we know that this is 0, this is 0, and the k's cancel out because it's k minus k, so constants are just going to cancel out. So we just have sine of pi over 2 plus pi over 2 times pi. Sorry, I don't know why I did that. Times cosine pi. Okay, so sine of pi over 2, that just equals 1. And then we have pi over 2 times cosine of pi, which is negative 1. So pi over 2 times negative 1, which means that we have 1 minus pi over 2, and that is the value of our fundamental theorem, or of our line integral over a curve. 1 minus pi over 2.